Yeah. Okay, so today's presentation is about DC-DC buck converter. So we're gonna see overview of DC-DC buck converter. Particularly, we're gonna see application of DC-DC buck converter in piezoelectric energy harvester. So firstly, let's talk about comparator circuits. What's a comparator circuits? The comparator circuits is a circuit which uses OPMs to compare between two voltages. One is input voltage Vin, and uh, analog. Another is a analog reference voltage Vref. So we are gonna compare between these two voltages, and depending on the comparison, the comparator circuit gives different outputs. So different outputs. And one type of a special comparator circuit is open loop comparator circuits, where the output voltage swings fully from the positive supply voltage plus VCC to the negative supply voltage minus VCC. So here's the details about the OPM comparator circuit. As we can see that if Vin is greater than Vref, then we have positive input is lesser than the negative input. In positive end we have Vn, and the negative end we have Vref. So if positive input is lesser than negative input, the output will be the negative supply voltage minus VCC. So which will result in negative saturation. In contrast, if Vin is greater than Vref, then the positive input is greater than negative input, and the output will be positive supply voltage plus VCC, and we have positive saturation. Theoretically, the output can range to plus minus infinity, but in practical, it's just the range actually looks like this, and the graph is somewhat like this. So about comparators, there are two types. One is non-inverting comparator. In non-inverting comparator, the positive side is connected to the Vn, and the negative side is connected. The inverting side is connected to the Vref, and so we have a graph that looks like this. As we can see, that if so this is the Vn, and this is the Vref, which is if R1 is equal to R2, then Vref is equal to VCC by 2. So we have an output that looks like this. If Vn is lesser than Vref, then we have 0, because the negative supply voltage is grounded, so the negative supply voltage is 0. And if the Vn is greater than Vref, as you can see in this part of graph, Vn is actually greater than Vref. So so the red line is Vref, and Vn is greater than Vref. So in this part, the output is plus VCC, as we can see in this graph. In the inverting configuration, the thing is basically exactly opposite. So Vin is now connected to the inverting side, Vref is connected to the non-inverting side, and the Vout is going to be exactly opposite to what we saw in the non-inverting comparator, exactly opposite. Now let's talk about the DC-DC buck converter. So here is the DC-DC buck converter that we're gonna that is used in the piezoelectric energy harvester. So basically, what we want to DC-DC converters actually provide a regulated output voltage from a given fixed input voltage. So in this case, we want to regulate the input side direct. So in future we want to use direct in the our piezoelectric harvester circuit, and we want to regulate this VREC using this DC-DC converter. So this converter regulates VREC from 2.2 volts to 5 volts with 4 bits of precision, and the power provided by the harvester is in the order of 1 to 100 microwatts. So it's a really small, it's a really small scale of power that we're talking about here. So what's the use of comparator in this circuit? So basically, so PFM, pulse frequency modulation mode of control, is necessary for achieving high efficiency for the really small microwatt level of power that is handled by this buck converter. So and this PFM control is actually obtained by this comparator that we can see right here. Excuse me. Yes, so this comparator right here. So this comparator right here, if we actually look into detail, then this is the discrete time comparator circuit we're talking about. So this comparator actually compares Vrect with VSTO, as you can see right here. So this is VSTO, and this is the Vrect. So this comparator circuit actually compares between these two, and if the Vrect turns out to be higher, the comparator sends a request box signal to the inductor arbiter to access for this shared inductor. So basically, what happens is that if a Vrect is bigger, then the comparator asks for access to this shared inductor, and if the access is granted through the ACK box signal that we can see here, and then the pulse width control turns the PMOS and CMOS power transistor on to actually with suitable pulse to transfer energy from harvester to CSTO. CSTO is right here. So basically, if the Vrect is higher, then this inductor will turn on, and there will be some pulse. There will be some suitable pulse and energy that will be provided to this capacitor CSTO right here. Reference ladder. So reference ladder is actually used to obtain the 4-bit precision of Vrect that we talked about. So Vrect can be expressed as 2 plus 0.2 times n, where n can be from 0 to 15. And then the reference ladder, this turns this into 1.8 volts. So VSTO is usually held to 1.8 volts, and reference ladder actually turns this into this. So this is the reference ladder circuit, and this is a simplified version of the reference ladder circuit that you can see here. So if we write the equation for the V out, it's simply a voltage divider. So we can write this equation like this. If we plug in n equal to 0, then with n equal to 0, then we can actually get this equation, which gives us z equals to 9y, and then we can substitute z equals to 9y to get this. And from here, we actually get x is equal to y. Therefore, x is equal to y equal to z by 9. So the current consumption by this circuit is 0.2 divided by y. And in often cases, we actually limit this current consumption. We actually fix this current consumption. In this case, the implementation was done such that the current consumption is 50 nanoamperes. So for 50 nanoamperes of current, we can actually determine the value of y. X is equal to y, and z equals to 9y. So we can actually get this resistance values right here. So then we get to zero current switching. So zero current switching is basically, for zero current switching is a kind of resonant converter. What is resonant converter? Resonant converter is an electric power converter that we include a network of inductor and capacitor that is made to operate in resonant frequency. So this is a converter which contains a network of inductor capacitor that is in resonant, that works in resonant frequency. So why is it used? So So switching devices, when they are used to turn on or off load current. So when they do that, so there is a high value of di by dt. So when there's a high value of di by dt, so there is a high voltage trace resulting in high power loss. So when the real value of di by dt is higher, the voltage trace is higher, so there is a high power loss. And also when we actually decrease the size of the components, the switching frequency actually increases. So there is even more power loss due to this. And also the high di by dt values can result in electromagnetic interference, as we can know from like Faraday's law and other Maxwell's laws. So the drawbacks can be dealt in a way that the switch of the converter to be turned on or off when voltage and current across the device will be 0. So when the voltage and current is 0, if we can turn the device actually on and off at that time, then we can actually deal with this problem, the high value of this di by dt or dv by dt. And for that, we use the zero current or zero voltage switching. Resonant converters actually work like this. There's a switching network which contains switching device like MOSFET or IGBT. There's a resonant tank, which is basically the network of inductor and capacitor, which are in the resonance mode. And finally, we have rectifier network. Rectifier network actually turns the so switch network actually produces a pulsating network because it is a switching device. The switch turns on and off. So the signal produced is a pulsating signal. So this pulsating signal is turned into a DC signal in this rectifier network. So here's the D to zero current switching. So how does this work? So S is the switching device, which can be MOSFET or IGBT depending on the frequency. LC, this is the resonant tank. So this part is in resonance. And this part, this DL1C1 part is basically the rectifier circuit. So in the steady state, what happens is that this current I naught flows through the load, and this I naught is a constant. So we can basically compare this as a current source because the current is not changing. And especially when this S is open, then this part of circuit is like basically gone, and this D also actually has a current of I naught flowing through it. So ID then becomes I naught when the switch is open. Now, what's the use of zero current switching in DC-DC converter? So as we can see here, so when Vrect is greater than VSTO, there is a signal sent to access the shared inductor. When the request is accepted, a PMOS on signal with pulse width TP is produced, which ramps up the inductor current from zero. As we saw that, I mean, there's a controlled suitable pulse signals that actually flows some energy, flows some current to the CSTO. So this is what's happening. When PMOS turns off, the NMOS turns on, it will be on. It will be on. So which ramps down the inductor current ideally. The ramps up the inductor current, ramps down the inductor current. Ideally, NMOS will turn off when the inductor current becomes zero. So we can actually, so the NMOS and the PMOS on times are actually related as follows. So the PMOS on signal actually is turning the inductor current, turning on the inductor current. The inductor current, it is making some current to flow to the inductor, and then the PMOS turns off, NMOS turns on, and then it again decreases the inductor current. And NMOS turns off when the inductor current again becomes zero. So the times, the NMOS and PMOS times are actually related by this equation. As you can see, it is actually a function of Vrect. We're assuming VST equal to 1.8. So if we fix TP, and if we just say TP is equal to 9 TD, then our TN is basically basically like this. And the pulse width control block then multiplexes the required number of TD delays to achieve zero current switching. Finally, there's this the efficiency equation for this DC converter will actually look like this. So here is the equation for the efficiency. Thank you. That's the end of the presentation.
Thank you. Let me share my screen. Here, how much VRAP? In here, VRAP is
VCC by 2. Yes.
But the smallest VRAP can be how much? Do you know? It can be 1 millivolt or 1 microvolt. How much? Which is the smallest VRAP can be?
That I don't know.
It depends on the
OPM.
PAM you design, the MOSFET you design. So, in here, the range is quite small, right? It's small range from 2 to 5. So your reference voltage is small range, right? But however, if your range is larger, like for example, 0.4 to maybe 10 volt or something.
Okay.
So it is more. So the reference voltage should be much smaller, right? It cannot be 1.8, right?
Yes.
Here is buck converter, so it should be larger than 1.8. It should be 2 volt and 2 volt. Maybe in triboelectric, it can go up to 70 volt, maybe. So when the range is larger, so the reference is also larger, so it will not be 4 bit, but you need more bits here. Did you try to understand this FET circuit?
No, I did not understand it.
I think now it's too early for you to try it because you don't study OPAM like you.
Yes, I will study it.
In this course, will you study?
We're gonna study OPM at the end of the course.
Yeah, okay. So now you don't study OPAM there, so you just need to understand that it just compare V in and VREF, and then the output is like digital. That's all, right? Later, at this moment, you don't need to design a comparator. I will provide you a comparator that I designed. In here, Y is 4 mega, isn't it?
It is Y. It's Y. It's better.
It is X is from here.
Yes. There is 9Y. So Y is 4 and
Y is 4, right? Z is 16, right?
9Y.
And X is from here to here, right?
Mm-hmm.
And it's controlled by 4 bits, right? Isn't it? So Y it is 50 nano ampere.
This is the implementation value.
Where it come from?
This comes from the power we want to provide.
Is current consumption, isn't it?
Yeah. Mm-hmm.
By 0.2. It is here 0.2 over 4 mega.
Mm-hmm.
Isn't it?
Mm-hmm. mean, we want 50 nanoamperes, so that's why we set Y to be 4 mega.
Thank you. 50 nanoampere actually the current flow from here to here. To ground, right? For example, here, like this is 5 volt, right? 5 volt. That's it one. Total here is evenly 3 plus 15, 8, 4, 15. Right, 100 meg. So it will be 50 nano, right? Isn't it? So when the voltage reduction change, the overall resistance also change. So it will be V ref, right?
Yes.
So the current here is the power consumption of this reference letter. So because we in microwatt, in here we just in microwatt level, so normally power consumption for later should be in nanowatt level. Actually, resonant converter we don't use in energy harvesting. Here is switching.
Those are the part of zero current switching DC-DC converter. That's why I started that part.
Yeah.
It's approximate zero current switching.
Here they don't show the inductor current waveform. Tn and Tp and inductor current, they don't show it. There are no figures, so Tp they don't show the current waveform and where Tp, where Tn. No figure here. Yeah, no figure like this. No figure show inductor current and then T1, T2.
No, there was no figure like this.
Do you know your current waveform in this paper? So
No, there's no
here is
figure.
operate in, you know, it have two mode is DCM and CCM, right? Do you know?
No.
CCM is continuous current mode. So inductor current will be always larger than zero, right?
Okay.
And DCM is discontinuous mode. So inductor current will be have a zero part,
Mm,
right? In here.
Yeah.
Current you should have figure like this, right?
but there was no figure like this in the paper.
Right. Do you really understand this? With
Yeah, I
the
understand that part, but the red line, the line I turned red, I did not understand. What is TD, by the way?
TD is the delay here.
Mhm.
TD. So one
Okay.
block is one TD, right? The delay time. So for example,
Mhm.
here 1 nanosecond, 1 nanosecond, 1 nanosecond. So here 1, 2, 3, 4, 5, 6, 7, 8, 9.
9.
It will be 10 nanosecond delay, right?
Okay.
In here 1, 2 will be 2 nanosecond delay. You got it?
Okay.
Yeah.
Okay.
So in here, actually they just control the delay time by, it's like here. It will short.
Mhm.
If we short this register, so it will be 0, right?
Mhm.
So in here is also shorted TD connect together,
Mm.
so it will become 0. So it can
Mm.
change your delay time.
Mm.
Or monthly. When you make presentation, you should not make too many words, and you should have figure to display, right?
Okay. Okay, okay.
So here, P mode turn off. This is P mode. Here is N mode. When countdown.
NMOS will turn
Here is
off, or turn on, by the way. It's a mistake. It's a
on,
mistake.
right?
It will be on. Yeah, yeah. I mentioned it.
First is the first, you know, buck converter, right? Two phase. The first phase is this, right?
Yes, yes,
Second phase is this.
yes.
The first phase is on,
Mm-hmm.
so inductor current is built up, right?
Mm-hmm.
And then in the second phase, this is off. Then inductor current will be ramped down until it reach 0 volt, right? However, because this change, so the time inductor turn on in here we fix is it fixed what? It's fixed TP or TD? Fixing TP.
TP is equal to 9 TD.
Here TP, right? TP, PMOS. And here TN,
TN.
right? TP here. So we fix it. But when this one change, TN will be changed, right? You have this. When you fix it, so TN will follow VRAC, right? Isn't it?
Yes. Yes.
So because TN change, so we also have to change the delay to make TN, right? This delay time will define the TN, the time TN, right? That is the reason why they make this delay. Did you got it?
Yes.
Okay. Actually, this is the most important thing in DC-DC converter. We always try to have high efficiency. Next week, we will simulate So next week we will simulate this part without control circuit, right? Here is the converter. And we control, first we will control gate, two gate by the load. Load is the output, right? There is restore. Restore. before I tell you how to calculate the power, right? Voltage multiply current, right?
Yeah.
So you calculate power and then you calculate the input power here through this node. However, actually, we have do you know the conduction load and switching load? You learned it before, right?
Yes.
Yeah, I think it's the energy loss in switch.
Conduction loss is the register, the parasitic register. For example, in inductor and in two switch, right?
Yes.
And in this simulation, your simulation already calculated. It become your thermal loss, right? It's,
Yes.
so the output will be input power minus conductance loss. However, you have to calculate switching loss. Switching loss is to turn on, turn off the two gate, right? Capacitor gate of MOSFET. It will be in here, in these two voltage source, right?
Yes.
Power will take from these two shorts to turn on, turn off these two MOSFETs. And we will have control circuit loss. Actually, it will become from this control circuit comparator and other things. But here we don't make control circuit, so now it's simply only have conduction loss and switching loss here.
Loss.
Only two loss, right?
What is E para?
It is parasitic.
Oh, parasitic resistance. Okay. Okay.
Is energy loss due to strain non-zero voltage swing at the rate. Maybe because when is turn on, turn off, not. So it might be because perfectly when this N mode turn on, this one should be turned off, right?
Yes.
But it's my some case that both N mode and P modes will be turned on at the same time, and so it will cause the loss, right? Anyway, we take control later. For your first simulation, just consider two loss, right? Two main loss. Conduction loss and switching loss will come from this. Okay, you got it?
Yes. Okay. Okay.
I will make the test pen anyway, and then you guys should change the CP and you fix TP and then you change TN,
TN.
to make different VREF, right? In my test plan, I will make only one case. For example, 2.2 to 1.8, but you guys should simulate all cases, right? You should change my shell and you should see how much efficiency will change, right?
Yes.
Okay, that is next week task and I'll type detail later. Right, let's share the screen.
Okay. You see my screen?
Wait, let me start that.
Okay.
Good.
Okay, can you see it?
Yeah.
So, in this short presentation, I'd like to share about circuit implementation of bias-sweep rectifier and something about boost and buck converter. The first one is the timing control circuit. As we can see in the left is the power electric harvester connected to the bias split rectifier. So we can still compare both to compare the VG reference and VHP and VHN. After we compare VH P and to the G reference and VHN with the reference, it came to the notch again to send the rush this signal. It came to arbiter, so arbiter can allow the connect to the okay the connect to the shader inductor. So initially we turn on the one and the V-high charge to the capacitor CD GD, and it's also something like this. So after we charge the VCD, is the switch one is turn on and switch two is turn on. So at that time we have this. So we can see that VG box is equal VGD plus VHN. Is the timing control circuits. Initially, we have the VHP almostly equal Vrest plus VD, and VHN is equal minus VD. So at the time, because VHP more than VDRES, so the output one either is a 0, and another because the voltage hash n is minus VD, so is the less than the V direct. So the output too is the higher. But when we train the current, we have a current came to the 0. So the V hash n it came to the minus VD. So it's less than VD. It's a more than VD, right? So R2 came to 0. So as we can see like this, after we compare the 0 with 0, so the not again there became 1. So we have the rush signal became 1. It can allow arbiter to allow access to the inductor sharing. Another one is the delay block to control the on time of bias flip switches. As we can see like here, is the input go through the delay block as well the move block. Visual move block with input signal is the C3, C2, C1, because when we can train the precision of the delay block by we push the signal such as 1 0 0 or 1 0 1 0 to the most block, so we can train the precision of the delay block. Also, we have delay 5 block. In this block, we need to track. Initially, we turn on or turn off of both the some of the switch in this slide is the F3, F2, F1, and F0. When we we turn on or turn off of this switch, we initially charge up to the CP, and when is the enough, it can lead to the delay of the output, and we can train the delay by training this capacitor, also the switch. In another right is a level converter circuit to shift the signal from V storage to the V high. The V high we can use to provide the power for the sub switch like this, either G switch top and switch bottom. The V high usually the 5 voltage. For example, we have the V storage, either 1.0 and V high the 5.0. When we push the 1, either high logic to the input, we have is the high. So these are MOSFETs is the turn on. Okay, so because it's the 1, so this is a 0, so it's a turn on. So we have the output signal connect to this is the 0. And when we put the 0 is the low logic to this, so it's the 0, so it's a turn on. And another one is a turn on, so output connect to this is the high signal. This is the way we convert the V storage to the V high, and this is the way when we change the 0 to 1 or 1 to 0, we can change the voltage of the output. It's a buck converter. It's a buck converter usually due to convert the fixed voltage to regulate voltage. But in this buck, we use to regulate the Vrex from 2.2 voltage to 5 voltage to the 1.8 voltage. Also, we use the pulse frequency modulation, the PFM. When we train the modulation, we can change the time that's PMOS as well the NMOS turn on with different the time delay. The time is the TP, is the TNs. So initially we turn on the PMOS, so the current flow like this. It charge up to the C storage, and it also ramp up the currents of the inductor. And when the PMOS is turned on, we turn on the NMOS, so the current flow like this. Okay, so at the time the current of inductor is ramped down. Okay, we can see like this is the current of inductor. Is the like this it's round up in the PMOS and the ramp down in the NMOS. Okay. So, okay, it's that I said that is the frequent pulse frequent modulation. It's usually the fixed on time and of the P and the variable uptime. In the P mode we use the fixed on time, and in the N mode we use variable uptime. When we measure the output voltage and we compare this with the V reference. If the V output is either less than V reference, is we generate this fixed pulse width generator. It generate the fixed on time, the fixed on time pulse to charge the C is a current flow like this to charge up the capacitor, and otherwise is if the V output is more than V rate, is the sum of this width is idling. It's not run. So switching frequency in the PFM proportional to loss current. So this is the reason why the switching loss is greatly reduced in a line load condition. So the PFM mode enable high frequency with Australia. It's a reference later that Ryan has said before. So I know present again. Okay. It is approximately zero current switching. We use this because before we turn on the PMOS NMOS, we need to turn off the before we turn on the NMOS, we need to turn on the PMOS. So we need to detect zero crossing. So after round up and round down, we need to have a delay. So the time, the ratio of the N mode and P mode on time is like this equation. It also be by fix the TP equal 9 TD. Okay, we have the Tn like this. This can be determined. We can train the precision of this delay by changing the logics of the VREG3, VREG2, VREG1, and VREG0. In this block is the 9 TP is the equal to TP. Boost converter is something like the buck converter, but it is just train the comparator is the minus and is the plus. But in the boost converter is the inverse. The arbiter block, arbiter will receive the signal from the rest proof and buck converter. Because we use inductor in threading, the arbiter control everything. When we receive the signal, is allow the share inductor share by using acknowledge track, acknowledge buck, and acknowledge book. Okay, thank you. So I have a question in this block. That is why we use the most block in this, and then why is the GND? I don't understand.
No. Yeah.
I just understand around this block is we changing the precision of the delay by changing the input of both, but in this I don't know what it is.
It's similar here, right? It should be like this, but why? Actually, multiplexer will select one or two, right?
Yeah.
VD is the select, right? Isn't it?
Yes.
So if here it can be VD or 0, right?
Yeah.
So if it VD, it will select 1, isn't it?
Yeah.
So all of them is VD. So it will be go like this, isn't it?
Okay.
But why they have brown here? For what? Which reason?
But it's not change the logic of the circuit, but why it's use for block of this mode.
If you look here, so it can be VDD, can be 0 or 1, right?
Yeah.
VDD is 0 or 1, and ground is 0, right?
Yes.
It will 1 and 0. So if here 1, it will go like this, right?
Okay.
And if control is 0, it will be like this. It's 0, and then it will remove the delay, right?
Yes.
But why here? In your thesis, they don't explain
Yeah, I don't
anything.
see the explain about this one.
So strange.
Okay, you hear me?
Yeah,
Okay.
I think first time I see. Anyway, just don't care. Anyway, we'll go this way.
Okay.
It's similar to here, right?
Yes, it don't affect the logic of the circuit.
Yeah.
Okay.
For PD, it is fixed. 1, 2, 3, 4, 5, 6, 7, 8, 9, right?
Yes.
9 T, and then TN is chain controlled by switch.
Yes.
Yeah, just don't care this. Just connect together. Okay, let me set swing.
Okay.
I think it's so. I have to simulate. Chain in the chain to control VRAM. I will make your one we ideal T N T T and pen. I will make it and send it to you later.
Yes.
And then see efficiency with that. And then so in your paper they also show efficiency in it. Right?
Yes.
Right? You should change VRAC and check it with here.
Okay. So change.
So we should produce the VDEC versus efficiency graph.
Yeah, you should make this graph.
Okay.
To check, right? You should make it.
Okay.
To check. The paper. So in here, they already provide your size, right? Switch size, right? There's PMOS size and NMOS size, right?
Okay.
1260 and what this mean? In here, we have 0.5, right? We have 5, right? Let's say one finger, so multiplier should be 126460. I think so. Should be a multiplier. Isn't it?
Okay.
It's too big. The maximum is only here, so it should be 10 finger and 126. Okay?
Okay.
The total multiplier will be 1260. Right? Here is a multiplier, this MOSFET. One MOSFET is 1/0.5, and it will be 126 0 it means it's like this. It will connect. Multiplier means on range source and gate will connect together, right? It will be 1,260 MOSFET will connect in parallel together. But if we connect like this, it will be really big, right? So it will make multiplier here. Got it?
Okay.
So you guys should also change the inductor value also, right?
Okay.
I think this week is okay. If we have more requests, I will tell you later. I should to make the test pen and check. Okay, I will send you maybe tomorrow or on Sunday. Okay, got it. Do you have any question?
No.
I have a question.
Yeah.
It's so short. Can I share my screen?
Yes.
Can you see it? It's slide. Can you see this slide?
Yeah.
Okay. When I read the book, I see some the circuit is so strange. So, for example, if this finger, what should I learn before background for to read understand the finger
This is amplifier.
amplifier? Okay.
You should read the amplifier in your book,
Yes.
right? If you have time, you should read it in advance because it takes a lot of time. So I cannot let you guys all the things, right? I just teach you guys how you with the work, and then anyway in the future you guys will learn it. So yeah,
Yes.
I should. Yeah, I have no time to teach you guys on the circuit, right?
Yes.
Yeah.
Okay.
So if you have just read it.
Okay. Thank you.
In advance.
Okay.
So you can Google it. So you, for example, let's Google it, continuous comparator on Google, and there is a lot of things in Google, right?
Okay.
You can read and check.
Just
Any question?
okay. No.
Yeah. Okay. Okay. Thank you. See you next week.
Yes. Have a good time.
Okay. Bye.
Goodbye, Supra.